Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on group lecture number 80, in which I will solve some problems on internal and external direct products of groups. Now we solve a problem. Problem is, if H and K are two subgroups of a group G such that G equal to H cross K. This is the symbol for G is isomorphic to external direct product of subgroups H and K. And we know that if G is isomorphic to external direct product of its two subgroups H and K, then G is internal direct product of subgroups H and K. Then H and K are normal subgroups of G, and quotient group G by H is isomorphic to subgroup K, and quotient group G by K is isomorphic to subgroup H. Now we prove this. Given that H and K are two subgroups of a group G, and G equal to H cross K. Practically, it is not possible that if H and K are two subgroups of G, and then G equal to H cross K, because each element of H cross K be in the form of ordered pair of elements of H and K, and H and K are subgroups. That is, each element of H cross K be in the form of ordered pair of elements of group G, and in left side we get only simple group G. So this cannot be practically possible, but this is a symbol. This symbol denotes that G is isomorphic to external direct product of subgroups H and K, and also G is equal to the internal direct product of subgroups H and K. Therefore, G is internal direct product of subgroups H and K. Therefore, number 1, each element of H, subgroup H, commutes with each element of subgroup K. Number 2, each element small g belongs to group G can be uniquely expressed as G equal to HK, small h belongs to subgroup H and small k belongs to subgroup K. Now, let us define a mapping phi defined on G, group G into subgroup H. Here group G and here subgroup H, and phi be the mapping defined by phi G equal to phi G means HK and this means H. Let this is number 1. It is clear that any element small h belongs to subgroup H. Here small h be an arbitrary element of H, we get an element HK equal to G of group G such that phi G equal to phi HK equal to H. Since H, small h belongs to subgroup H, small k belongs to subgroup K, and subgroup H, subgroup K are subsets of group G, implies that small h, small k belongs to group G, implies that HK belongs to group G. Therefore, phi is onto mapping. This is number 2. Now to show phi is homomorphism, let small g1 equal to h1 k1, small g2 equal to h2 k2 be any two elements of group G. Now phi G1 G2 equal to phi G1 means H1 K1, G2 means H2 K2. This equal to phi here H1 K1 H2 means H2 K1, since each element of subgroup H commutes with each element of subgroup K. This is by using 1. And this equal to H1 H2, since H1, H2 belongs to subgroup H implies that H1, H2 belongs to subgroup H by closure property. This equal to, we may write H1 equal to phi H1 K1 and H2 means phi H2 K2 and this equal to phi G1, this is phi G2. Therefore, phi is homomorphism. This is number 3. Therefore, phi defined on G, group G into H is onto homomorphism. Here group G and here group subgroup H and this is phi mapping. E be the identity element. Let E be the identity element of H means subgroup H. This identity element is the identity element of group G. So this is the identity element of group K also. Kernel of phi equal to all those elements of group G. This is car phi whose image are identity element of subgroup H. Let G belongs to group G such that phi G equal to identity element of subgroup H. Let this is number 4. Since G belongs to group G is the unique product of an element of subgroup H and an element of subgroup K and image of each element of car phi is identity element of subgroup H. Therefore, phi G equal to phi G be the unique product of an element of subgroup H and an element of subgroup K and image of this is E. Therefore, here will be E and here an element of subgroup K implies that phi EK means K identity element and element of K is element of K equal to E for all small k belongs to subgroup K. Therefore, kernel of phi is the subgroup K. This is number 5. Since kernel of phi is a normal subgroup, of group G. Therefore, subgroup K is a normal subgroup of group G. Since phi defined on group G into subgroup H is onto homomorphism with kernel of phi equal to subgroup K. Therefore, by fundamental theorem of homomorphism, there exists G by kernel of phi which is isomorphic to subgroup H. There exists a mapping psi defined on group G by car phi into H is an isomorphism. Implies that G by kernel of phi is isomorphic to H. Implies that quotient group G by kernel of phi is subgroup K is isomorphic to subgroup H. Proved. In the similar manner, we may prove that H is a normal subgroup of group G and quotient group G by H is isomorphic to subgroup K. Now we solve a problem. Problem is a group G is the direct product of its two subgroups H and K if and only if number 1 H and K are normal subgroups of group G. Number 2 H intersect K equal to a set containing only identity element. Number 3 G equal to HK. Now we solve this. Since given that H and K are subgroups of group G and let 1, 2 and 3 holes let small h belongs to subgroup H and small k belongs to subgroup K. Implies that H inverse belongs to subgroup H and K inverse belongs to subgroup K. Implies that H, K, H inverse, K inverse belong to group G. Since H and K subgroups of G are subset of group G from 1 H be normal subgroup of G. H is a normal subgroup of G, implies that K H K inverse belongs to H. Since small h belongs to subgroup H and K belongs to group G, implies that K H K inverse, here H inverse belongs to subgroup H, because this part belongs to subgroup H and H inverse belongs to subgroup H. So by closure property we get this part, operation H inverse belongs to subgroup H. This is number 1. Again, from 1 K is a normal subgroup of group G. Since small k inverse belongs to subgroup K, implies that H small k inverse H inverse belongs to subgroup K, means K is normal subgroup, K inverse belongs to subgroup K and H belongs to group G, and then H inverse belongs to subgroup K, implies that if we take here K H K inverse H inverse, this part belongs to subgroup K and small k belongs to subgroup K. Therefore, by closure property, this element belongs to subgroup K. This is number 2. From 1 and 2, we get the same element belongs to H and K. Therefore, K H K inverse H inverse belongs to H intersect K. This is number 3. Since from 2 here H intersect K contains only identity element. This is number 4. Therefore, from 3 and 4, we get K H K inverse H inverse equal to identity element, implies that K H H K whole inverse equal to identity element, implies that K H H K whole inverse operation H K equal to E operation H K, implies that K H HK whole inverse operation HK is the identity element equal to identity element operation HK is HK implies that KH equal to HK. This is number 5. Since small h be an arbitrary element of subgroup H and small k be an arbitrary element of subgroup K and from 5 HK equal to KH. Therefore, each element of subgroup H commutes with each element of subgroup K. Let this is number 6. Since from 3 G equal to HK, therefore for any small g belongs to group G, we get G equal to an element of subgroup H and operation an element of subgroup K, where small h belongs to subgroup H and small k belongs to subgroup K. Let this is number 7. If possible, let G equal to H1 K1. H1 belongs to subgroup H, K1 belongs to subgroup K. Another representation of element G belongs to group G. Let this is number 8. From 7 and 8 we get HK equal to H1 K1 implies that H1 inverse HK, here K inverse, here H1 inverse H1 K1, here K inverse implies that H1 inverse H K inverse, this equal to here H1 inverse H1 K1 K inverse implies that H1 inverse H K inverse is the identity element equal to H1 inverse H1 is the identity element and here K1 K inverse implies that this will be equal to H1 inverse H and E operation K1 K inverse equal to K1 K inverse. Let this is number 9. Since H1 inverse and H belongs to subgroup H implies that H1 inverse H belongs to subgroup H. Also, K1 K inverse belong to subgroup K. By closure property, K1 K inverse belongs to subgroup K. This is number 10 and this is number 11. From 9, 10 and 11 we get H1 inverse H equal to K1 K inverse belongs to, these are same element and these belongs to H, subgroup H, also in subgroup K. That means they belong to H intersect K. Let this is number 12. Since from 2 H intersect K contains only identity element, therefore H1 inverse H equal to identity element and K1 K inverse equal to identity element, implies that here we take operation H1 inverse H equal to H1 identity element and here we take operation K equal to EK, implies that H1 inverse associative property H equal to H1 identity element is H1 and here we take associative property K1 K inverse K equal to E operation K is K, implies that this is identity element H equal to H1 and K1, this is identity element equal to K, implies that H equal to H1 and K1 equal to K, implies that H1 equal to H and K1 equal to K, implies that H1 K1 equal to HK, which is G. This is number 13. From 13 we get that any element small g belongs to group G is represented uniquely as a product of an element of subgroup H and an element of subgroup K. This is number 14. Therefore, from 6 we have seen that each element of subgroup H commutes with each element of subgroup K. Therefore from 6 and 14 we get that G is the internal direct product of subgroups H and subgroup K. Proved. Conversely, let G be the internal direct product of subgroups H and K. Let X belongs to subgroup G. Therefore X is uniquely represented as product of an element H of subgroup H and an element small k of subgroup K, that is X equal to HK. Let this is number 15. Let A belongs to H. Now X inverse equal to X is HK, A HK whole inverse, and this equal to HK A K inverse H inverse equal to H A K inverse H inverse. Since each element of subgroup H commutes with each element of subgroup K, here we have KA and we have written here AK. Implies that X inverse equal to H A K inverse equal to identity element, and here H inverse, this equal to H A H inverse, this belongs to subgroup H. Since H A H inverse all are elements of subgroup H, and by closure property this belongs to subgroup H. Therefore H is a normal subgroup of group G, because X belongs to group G and A belongs to subgroup H, and X inverse belongs to subgroup H. That means subgroup H is a normal subgroup of group G. One part proved. In the similar manner, we may prove K is a normal subgroup of G. Therefore, 1 is proved. Now let B belongs to H intersect K and B not equal to identity element implies that B belongs to H and B belongs to subgroup K and B not equal to identity element. Since H and K are subsets of group G, therefore B belongs to group G and B not equal to identity element. This is number 16. We may write B equal to EB, E operation B. E belongs to subgroup H and B belongs to subgroup K. Here B belongs to subgroup K. This is number 17. Also, B equal to BE. B belongs to subgroup H and E belongs to subgroup K. This is number 18. From 16, 17 and 18 we get B equal to E operation B equal to B operation E. B is not identity element. Therefore, B belongs to group G is represented as product of elements of H and K, subgroup K, in two ways, which is against the definition of internal direct product. For group G. Therefore, our assumption B not equal to identity element is wrong. Therefore, B equal to identity element. Hence, H intersect K contains only one element, B equal to identity element, that is H intersect K is a set containing only identity element. Therefore, 2 is proved. Let small h small k be an arbitrary element of HK, that is HK belongs to H subgroup K, small h belongs to subgroup H, small k belongs to subgroup K. This is number 19. Since subgroup H and subgroup K are subsets of group G, implies that small h, small k belongs to group G, implies that H operation K belongs to group G. This is number 20. From 19 and 20, we get HK is subset of group G. This is number 21. Now let small g belongs to group G and group G is the internal direct product of subgroups H and K. Therefore, G is uniquely represented as a product of an element small h belongs to subgroup H and an element small k belongs to subgroup K. That is G equal to HK. H belongs to subgroup H, K belongs to subgroup K, implies that G equal to HK. Here HK belongs to HK. This is number 22 and this is number 23. From 22 and 23, we get G is subset of HK. This is number 24. From 21 and 24, G equal to HK. This is 25. Therefore, number 3 is proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.